Right now we need to switch over to the panel session. So we're going to Phil Evans, Diederichs, Zbyszek, Otwinowski, and Jim Pflugrath up here for a panel session. We're going to talk about what exactly people should be putting in, or how should they display their Table 1 statistics. I know some people are a little apprehensive about using Table 1 as a noun describing their data, but that's what we're going to do today. So I put up a table here. This is kind of a mix of a table. Some of the parameters are hidden from a discussion I saw years ago. But some of the numbers that look maybe a little bit out of place are from a paper that was just published this month. So right now we're not really going to focus too much on the numbers, although they may come up. The statistics that are listed are what are kind of the minimum of what are required for publishing. So we're going to figure out what is missing out of this table, why, and what else should be included. And this guy's here to start. And the table is also right in front of you. I have an extra copy right here on the paper.
Well, I'm happy to start, actually. This is first up publication, right? So the various programs will produce a Table 1, and as you can see from the display up here, it does show things in the dollar resolution show overall. The multiplicity is here, the completeness is here, the average I over sigma is here, the number of protein, and so on. I was mostly concerned with the early stuff here. And it doesn't show the total number of reflections, does it? Observations.
Reflections.
So you would have to calculate that. So I would probably show the total number of observations myself. And so it would be 22.5 times 98,000, right? It doesn't show an R measured as already, and I would show that. If you were using anomalous data to solve the structure, I would show an R measured anom, for example. It's hard to know what's going on there. The I over sigma here is interesting. The way that the table is shown, the sigma, as Kai said, can be calculated in many different ways. And in fact, you can change by changing the error model scale path. You can multiply all the sigmas by 0.5, right? Or by 0.1, and that will change your I over sigma. There's no requirement in Table 1 to show something like a reduced chi-square to let you know that the sigmas are legitimate. You can actually cheat on here. People say, oh, I over sigma 50. And there is no way for a reviewer to verify that. I'll stop there and I'll let somebody else.
Okay, I can say something. So what, so many points here. I mean, first of all, why are we having this discussion? It's probably a question more to you, because, I mean, are we in a position to influence what the journal's policy is? That's the first thing. And the second thing is, we all also depend on the PDB and that they change their procedures. And I find it very terrible that they don't have, let's say, they don't ask about CC1/2, they don't ask about RBs. It's just like the science being done 10 years ago, and they are perpetuating this. This is what makes me angry, and we can discuss as long as we like here for more than 20 minutes, this won't change anything. So is there anyone in the audience who has the power of changing anything? Or is the intention to find out for the next paper?
Let's assume that we can change it.
Okay. my dream Table 1.
I mean, you can still add those to the journals in your table. It's just that they're not required.
PDB won't take anything. And in fact, they always go above 150%. At least in the position I use. Anyway, I'd like to backtrack off that a little bit and say who is supposed to be reading the table 1 and what are you supposed to take away from that. And there are two audiences. One is the referee, and this is, for the referee, this is really inadequate information to tell anything. And I really like some maps, actually. As far as the reader is concerned, it's also, at least, okay, the statistics you've got on the data processing, the main purpose of that is to show, is this a good data set or is this a bad data set? And the trouble is, this doesn't distinguish between somebody who's made the best of a bad job, basically, got a pretty bad crystal set, managed to extract something decent out of it, and another author who really has been a bit casual about the data, maybe is rather wishful thinking about what they can extract. And the trouble is, it's very, I mean, these sort of statistics don't really tell you any of this information you actually want to know, which is how reliable is a particular, in the end, what you want to know is that somebody has decided that there is a hydrogen bond between this bond in their ligand and the residue in the protein. And no data processing is going to tell you that. No global refinement statistic is going to tell you that. What will tell you is an unbiased map, actually. And that's not for use. So I'm not sure whether, I'm not absolutely convinced the table 1 has any great value at all. Let's see if you
I would like to add something to this table 1, something of very different character. So one thing is that to quantify one way or the other extent of radiation damage during data collection, because this is very useful. Essentially, what type of radiation dose the structure corresponds to, essentially. And what was the maximum radiation dose in the experiment, which is not the same thing, because it's very swaying. Typically, I would say that the effective dose would be about 1/3 or so of the full dose. Say, as a rule of thumb, as we speak. At least full dose is easy to get, at least in terms of, say, increase in action square or change in the structure factors. Because there are two ways to quantify radiation damage, by decay and by changing structure factors after decay correction. So those are two fairly critical aspects for some projects. And as far as projects may not matter. So this is one thing. The second thing I like to show, because it's, I need to, if you can show my presentation, I have some extra slides at the end. Because this is to do with the CC1/2, in fact.
Which one is it? This one?
Yeah. No, this one. This one. Just the exercise after. Because the thing is that what I noticed is in refinement, there is a plateau in terms of artery. So this is it's an intermediate resolution. So it's high at low resolution, then it gets to plateau, and then goes up again at high resolution. And I would like to have the information at what resolution it increased by a factor of about 1.4 times plateau. Which is this is the resolution where experimental errors are comparable to model uncertainty. Essentially, this is what we call effective resolution of our data. Because there is some extra information past the resolution limit. Because but it starts to become definitely fractional because our predictions are better than in accuracy of the model. So, the last.
Did you say already one?
Okay. So this is, for example, one of the slides, which is this plateau is not. This was extremely high resolution data, but you see it was pushed way past. The plateaus here around 60% are free, I think. And I would say effective resolution was something around 0.75. Say, but again, kind of something which is mine. I did the refinement for 2 different ways, and the last refinement also was kind of higher free, was something like 6 or 7% in the intermediate zone here. And then I think this 1.1 was effective resolution, where CC1/2 was about 99%, 90% at least. It's because it's the lower free, essentially the data which are noisy are not very informative because the model is more accurate. So essentially then you don't have much of new information. It's kind of going down to CC1/2 is useful if your models are not very accurate. Like, this was probably better than a typical model. But this carrying this information where we reach this kind of point of error, experimental error being as big as model error, is going to be kind of interesting to know.
So where is this point?
Oh, this depends, of course, on this resolution dependence of R3, or even R3 defined.
So, yeah, that's a good point, but I think what interests most people, also if I look at CCP4 bulletin board discussions, is what is the resolution of your data?
No, but this is the answer.
Yeah, okay, but I don't see any formula or any easy way.
Because this is an effective informative resolution in a sense. This is a resolution where experimental data are more accurate than model error.
So you set 1.4.
It's a bit lower than the limit of your data. You see, there are two things. Where the data kind of last observable, which is used to end, versus where is kind of effective resolution where you still the data kind of define your model. So this would be lower resolution than the limit of your data. Which I still use. So it's not useful in terms of, you have to learn kind of, it's like if everything, it's a kind of statistic which is where it's an average. It's going to take, it will take time to get accepted, but this is the resolution which really tells you, how good are your data.
So we call it effective resolution then?
So essentially this is
Yeah, how do you define effective resolution?
well, essentially 1.4 times increase times plateau. So
The lowest are free.
The lowest are the shells, and then increase after the variance increases by 2.
This is at variance to what has been published so far, right? I mean, you need to write a paper about this and to show this.
No, but this is something that I we directly are really trying to go for refinement to see.
I think there's another point about the effective resolution or the cutoff is that it isn't that critical. The difference between a structure of 2.0 and 1.9 or 2.1 is marginal.
It still has to, you have to say something for the reviewers.
The reviewers get much too uptight about these things. and it is our duty as authors to argue with reviewers.
Speaking of reviewers, I was asked to review a table 1 recently by another reviewer. And what was going on is perhaps one of your papers, actually, that, to my knowledge, was not accepted. So they were trying to figure out what the true space group was. And they hadn't, it was one of these early crystallization papers, so I don't think the structure was known at the time of this write-up to get something staked out. And looking at the table 1, they did show that they had collected images every 1 degree, but they also had a very, very large unit cell, something like 200 by 200 by 200, and a wavelength that suggested that all of the reflections at higher resolution will probably overlap because of the way the data was collected. So what happened in the table 1 was that the completeness fell off at high resolution, right? So Raj is nodding his head. You know from the geometry of the Ewald sphere in that construction, you can see what's going on. And it turns out that probably at lower resolution, the model in the unit cell was whatever it was, but with the higher resolution, there was some breakdown in symmetry also. And from the data that was shown there, and interleukin 1 beta is an example of this as well, at low resolution, say the space group was P4 sub 1, 2, 2, but at higher resolution, these 2 folds broke down, and it became P4 sub 1, and then added onto that with some twinning and so on. So in this case, from the table 1, you could not unambiguously, I think, agree with the authors what the space group was, in fact. And it was partly, there were some clues there. If they hadn't told you that it was 1 degree per image, you wouldn't have a reason to try to figure out why information was missing. And certainly it's geometric, but so even at the high resolution shell, I think you should have better than 95% completeness. It's possible to say I solved the structure to 1.5 Angstrom resolution using 50% completeness in the outer shell. There's nothing wrong with that. but I wouldn't put in my title of my paper that it was a 1.5 off structure unless my completeness was higher. So there are some clues in the table 1. Whether the reviewers catch them or you catch them before you put them in there, it's you know, it's hit or miss, I guess. The other thing, going back to the PDB, the I over sigma for scale pack, which is the average I divided by the average sigma, is quite a bit different. Even though he says it's the same, it's quite a bit different than the average I over sigma. The average I divided by the average sigma is always higher than the other one. So in the old days, people would say, why does scale pack always give me a higher I over sigma? Well, it's because I'm using a different formula for I over sigma. It is. And you can just do that. You can take the same data. You know you can do this no merge original index out of scale packing. You can plug it into statistics calculated in other ways. You can compare apples to apples, and you can actually see that it's physically different. The PDE folks, to my knowledge, make no distinction. They just assume that you've reported the correct I over sigma. There is not a field for average I divided by average sigma, and a separate field for.
They don't define what they want.
Well, they don't know. Because we haven't told them what they want.
First of all, it's something strange what you said. You don't need unmatched data for a grade. You just have to, because it's statistics of matched data. So this is, there would have to be really like variation. I think this was out. The issue is essentially, like CC1 half assumes that errors are almost essentially about the same. If your data was largely engaged, not listening, it maybe even underestimate quality of data. So, because it's some large data with large errors will kind of contribute to poor CC1 half, even if average data will be okay. It's also this completeness, is it in the sense of Bragg law, or completeness in the sense of informativity, say like elliptical resolution. The word completeness is not very well defined, and in fact, in programs like C-truncate or C-truncate remove what they call uninformative reflection, but use somewhat different criteria. So definitely some reflection is lost during intensive structure factor conversion.
And use that very negative.
No, this can be the average expected density is low. So there is some kind of informativity effect there, like sigma to expected density.
It is, yeah. C-truncate does reject all shell reflections in a week.
If you have a reflection which is negative, less than negative minus, minus 4 sigma.
No, it's not different criteria. It's the sigma is too high relative to expected density. So the completeness from Verfmark is not the same completeness from scale pack, because in between there is a, even if you don't use the autocorrection, in between there is a program like C-truncate, which will remove some reflection.
So let's switch gears a little bit. We're actually running a little bit late, but does anybody in the audience have any questions on any of these things?
Okay, how do you handle anisotropic data in table 1? And let's say highly anisotropic, not like the one in the exam. As a reviewer, not as an author. What you would add
as a reviewer, so first of all, this doesn't have any information about this, so it's a good idea to add maybe, let's say, the B11, B2, B3, so these three main direction B factors, or whatever you call them, should be added to the table at least if the data are anisotropic. That would be a good idea, I think, so that the reader or reviewer get the idea that yes, these data are anisotropic. Other than that, I would say that anisotropic data are not a problem per se, because the refinement problems nowadays take care of that.
All the statistics will be distorted by anisotropic data.
But I would just say show two R measures, one using some of the soil thing and one showing everything. They're users can decide what they want to do. So in the outer shell completeness, you could say, here's the number of reflections greater than 2 standard deviations, for example. And I just put more information there rather than less information. And as a reviewer, I go, oh, okay, that's cool. I accept that it's anisotropic. Good luck to these guys.
Okay, what about number of parameters, number of observations? Let's say I have NCS factor 12, and then there is another structure which has NCS factor 1. Obviously, the information content, if I use NCS, will be different for those 2 structures. So how to put this in the table? I know that this is already beyond the data processing, but to some extent, this is never finishing in the table either. So I would like to have it too.
The anisotropy can also be expressed as a resolution estimate in different directions on the criteria. And it doesn't matter what the criterion is really, because what you want is the relative one. And that's kind of discussed that.
But if he said that we can change something, this is actually where I see mostly where the reviewers complain. They don't understand the anisotropic resolution, so they don't understand why somebody cut data to I over sigma, let's say 0.5 or whatever. And basically, I would like to, I don't know if any program currently prints out the anisotropic resolution, because I know that ScalePack AMS does. Okay. So this could be reported. Actually, ScalePack prints out too, but not directly, so.
But it's easy.
Any other questions?
So for me, like the table 1 is more like overall evaluation about the structure. But on the science part, I think 90% times we are focusing on just like an active site pocket or interaction part. But that's not related. I mean, as correlation coefficient is very low. If you compare your local structure confidence and with the overall structure. So is there any way we can add in some like new parameters or index just focusing on the local structure reliability?
Well, I mean, if you think about it, you have the whole
Besides
structure.
the density, actually.
You have other issues that you solved that were incorrect that would make your local part not correct. So if you, like, say, for instance, pseudosymmetry, which happens all the time, you would assume the wrong higher space group so you get the average in what your active site is, whereas actually if you have more than one molecule asymmetric unit, they may have different shapes in your active site that may give you more information or more details, and you wouldn't see that.
Good. Yeah, I agree that part. I just want to compare because I saw something like a 1.5 resolution angstrom data, and the other guy saw something like a similar. But I don't want to do like a compromise, like to try to make my table 1 looks beautiful. But I got all three something like a 1.7. The other guys is much better than me, but that does not mean that the active side he presents is better than me. I just want finding something way to like compare like which structure on that particular side is more reliable.
So yes, that's easy before ED starts, and you can look at the electron density correlation coefficient. That is, I think, one good way.
One simple addition to that table is the mean B for the ligands.
What's that?
The mean temperature factor for the ligands.
Okay, I think that's on there.
But actually what you want to see is an emit map for the ligand. To see what the ligand is really there.
Yeah.
And how reliable it is.
Yeah, the chances are that the other person with the better map cheated. Yours is better anyway, right? So you have to go in with that confidence that 5 years from now that their PDB deposition will be retracted. Standing alone with the right structure. There are these validation tools that are available now for that, and that's what I think we would use
So
for
the
this
PDB
local
won't
stuff.
attract anything.
I have one more point. I think we'll have to live with the PDB for now, and we can think about all different kinds of additional indicators, as Zbyszek said, informativity of reflection. I don't know what he means, but there are probably good ideas around. The one possibility that we have to come up with good ideas and use them for data that we have, or use them in the future for data that we have now, is deposit unmerged data with PDB. And that is,
So make it really hard.
supposedly it is already possible, and if we as an audience or community start to press in this direction, they will make it easier. And I think PDBE, the European, is already willing to accept. So that is what the people from JCSG also claim. They seem to deposit always the
Yeah, but they deposit out most of the information. They deposit unmerged data, but they lose half the information about the crystals and the geometry information. And the JCSG ones are
But having the unmerged data would allow to come up with all these anisotropy parameters. It would come up, it would allow to get this informativity or whatever you can come up with in the future. Whereas if you merge, merge data, all of this is gone. Yeah? So it would be a tiny amount of more work on our part, or PB, but it would help us a lot in the long run.
So, let's thank the panel for going over this.